Hello, my name is Liam, and today I'll be presenting our paper RAID, a shared benchmark for robust evaluation of machine-generated text detectors. So, it's well known that humans have a very difficult time distinguishing between text written by a large language model and text written by a human. And this is bad because it opens up the door to a lot of harmful applications of large language models, namely phishing scams, information pollution, fake product reviews, scientific fraud, so on and so forth. And so one would think that we would really like to be able to detect between machine-generated text and human-written text. And in fact, if you check the literature, this is very common and, in fact, a very easy problem. We see that accuracies are 95% or higher very commonly, and hooray, so we're good. The problem is that the boots-on-the-ground reality of this is a lot muddier. We see that companies are regularly pulling their detectors due to low accuracy. We see studies with theoretical claims saying that reliable detection of generated text is impossible. And we see testimonials from people saying that they've been falsely accused of using machine-generated text in their assignments and their professional work. So why is there such a problem? We claim that this is because there's a lack of evaluation on shared resources. In our view, this leads to overclaiming of detector performance and undertrusting of those same results. We also think this leads to fatalism around detection, so a questioning of whether or not detection is even possible, and it also leads to methodological confusion, which is to say questioning what the correct way to detect generated text actually is. And so to combat this, we introduce RAID, the largest and most comprehensive benchmark for detecting machine-generated text. RAID includes over 10 million generations, which is roughly 2 orders of magnitude larger than the next largest dataset, and it spans 12 generative models, 11 textual domains, 4 decoding strategies, 12 adversarial attacks, so on. Using RAID in our paper, we benchmark the performance of 12 state-of-the-art detectors, 4 from each different category, and we'll present the results here. A quick overview of what's included in the RAID dataset. We have models that span from large to small, open source to closed source, and chat and non-chat. And for our domains, we have a couple of the more commonly used domains in detection, such as news and paper abstracts, but we also include domains that are a lot less common in detection benchmarks, such as poetry and recipes. We're also the first dataset to include variation across repetition penalty and decoding strategy, and we also test the largest variety of adversarial attacks. In this talk, for time purposes, we can only go over 3 major findings. Highly recommend, of course, that you read the paper to see more, but for time purposes, let's go on ahead, starting with the finding around false positive rate. So, false positive rate is the rate at which you're incorrectly identifying human-written text as machine-generated. Detection, much like other binary classification tasks, goes off thresholds. So if we set our threshold very low, we'll get a very high true positive rate, so we'll detect a lot of the generated text, but we'll also get a very high false positive rate, which is that we'll misclassify a lot of human-written text as machine-generated. As you raise this threshold, this trade-off, our accuracy goes down, but our false positive rate also goes down. So our ideal operating point is actually here, because a false positive is very damaging in the detection space most of the time. Say if you're a student and you're incorrectly accused of having used machine-generated text, you may fail the class, or if you're a journalist, you may lose your job. So we'd like to find out what the false positive rates of our detectors actually are. And so here we track the accuracy with respect to false positive rate for all of the detectors and find that detectors are able to achieve 90% accuracy or higher, but only at similarly high false positive rates. Likewise, if you go to the low side of the spectrum, no models are capable of operating well at a safe false positive rate. We see very few of them get higher than 50% accuracy. And this is a problem, because typically a lot of detectors do not report false positive rates and only report accuracy. And so we're calling on a lot of detection researchers to amend what sorts of evaluation metrics they're using, because false positive rates are very important. Okay, the next finding is that detectors can have holes in their coverage. Really quickly, because it's important, a decoding strategy is just the way that you pick the next token from the language model output distribution. In greedy decoding, we're always picking the most likely token, and in random sampling, we're sampling directly from the language model's probability distribution. Furthermore, a penalty or some other alternative decoding method is just modifying the output probability distribution of the language model. So in this case, we're downweighting the probability of the tokens that have previously been generated. And we find that this is very effective across all detectors in terms of fooling them. in this chart, we have the 3 different categories of detectors, and we report the average performance at a false positive rate of 5% for each of the different decoding strategies. And we find that you can get roughly a 30% decrease when moving to random sampling, and then another 30% decrease on top of that when adding a repetition penalty. Furthermore, we find that many detectors fail on particular generators and domains, so they have particular weaknesses. In the case of the OpenAI GPT-2 detector, it's really only very good at detecting GPT-2 and fails for all of the other models. GPT-0, on the other hand, focuses a lot on the OpenAI models, so ChatGPT, GPT-4, but is relatively weak on the other open source models. And finally, Radar is really weak on a particular domain, that is to say movie reviews. Combining both of these results, we see that seemingly really strong detectors can sort of degenerate into failure very quickly. The following is the top 5 detectors for the news domain, fast detect GPT, originality, binoculars, so on and so forth. And we see that while they normally perform very, very well, on certain combinations of models and decoding strategy, they can perform basically 0% accuracy. And this is really problematic because a lot of the detection datasets don't have a large enough selection of generators and domains to properly capture these holes. Finally, let's talk about adversarial attacks. So I'll give you a second to figure out what the difference is between these 2 pieces of text. And if you said that this has extra white space, you'd be correct, but you'd probably also be interested to know that this causes roughly a 15% decrease in performance on average across all detectors tested. Similarly to the white space addition attack, there's a lot of other very small, very insidious attacks that cause a very large decrease in performance from detectors. Article deletion attacks, uppercase, lowercase swapping, and then the more traditional attacks such as paraphrasing and synonym swaps. One attack that we'd really like to highlight is the homoglyph attack, that is to say swapping characters for similar characters that look very similar but are different Unicode IDs, so the E and the I from the Cyrillic alphabet, for example. And on average, we see that despite what you may think, the attacks that are the small edit distance attacks that attack the tokenizer tend to be more effective than the attacks that change the semantics of the text. In particular, the homoglyph attack is extremely effective. And if you break down the performance across detector classes, you'll see a lot of interesting trends appear. For example, the metric-based detectors, such as GLTR and binoculars, are unusually sensitive to the synonym attack, whereas most other detectors can handle that attack perfectly fine. In addition, you'll see that the neural methods are really robust to the paraphrase and synonym attacks, and they actually get higher performance with the attacks than without them. Finally, we see that all detectors are extremely weak to the homoglyph attack, all except GPT-0, which leads us to the next point, which is that Radar and GPT-0 are actually surprisingly robust to a lot of attacks. Radar, we know, has undergone special adversarial paraphrase training, and GPT-0, we can speculate that potentially there's some text normalization involved. But our point is to say that it's not impossible to make detectors robust to these attacks if you specifically train for them. And we call on detector developers to do more to train on adversarial attacks. Anyway, what are the main takeaways? So, in our view, detection is neither solved nor impossible. It's actually just somewhere in the middle, and that's fine. And we want to figure out where in the middle detection is so that we can improve our detectors. And in order to do so, we just need better transparency and better standards. We need to know which domains and models have been trained on. We need to know what the false positive rates are for our models. And we need to know what adversarial training these detectors have undergone and what attacks we can expect the model to be robust to. How can you help with this? You can use the RAID leaderboard and evaluation suite to evaluate your detectors and to consult for what the up-to-date information is on how robust these detectors are. We've built a PyPy package to allow for ease of evaluation. All you have to do is submit a pull request to the repository and we'll automatically calculate your evaluation metrics. Thank you so much. Please check out the leaderboard in the paper if you have time. And again, thanks for listening to this talk.